Welcome to March 16th LeetCode Challenge. Validate stack sequences. Given two integer arrays pushed and pop, each with distinct values, return true if this could have been the result of a sequence of a push and pop operation on an initially empty stack, otherwise, or false otherwise. So we have the inputs here being pushed, such as this array here, integer array, and we have popped being this array as well, and we return true because we are able to this could have been the result of a sequence of push and pop operations, that being such that here's how we do it. So basically we push 1, push 2, push 3, push 4, then we pop 4, then we push 5, then we pop 3, pop 2, pop 1. So basically, we develop a stack, and we push and pop, and then we end up with the pop stack, and therefore we are able to make a sequence of results resulting in push and pop operations on the initially empty stack. Right? And this one, false, because when we get to 1 here, it's not possible to pop it before 2, because 1 comes before 2. And there you go. So the length of the operations, push length is between 1 to 1000, pushed and indexed between 1 to 1000. All elements of the push are unique. This is good. We need this right here. Pop length is equal to push length, which is good as well. So ensuring that both the pushed and pop length are the same. Pop is a permutation of push. Wow, this is. Thank you for that. So it's just saying that it's the same number, same unique values, same length, just out of order, and we just got to determine whether it's a push and pop operation that's initially on an empty stack. So in order to do that, let's, I ran some test code earlier and it seems like it's working, so let's kind of think the idea through. So we're going to iterate through the push stack, and we're going to validate it basically by using push and pop operations. And the first thing we want to do is define a stack. So define a stack, and that's going to be, however, it's going to be a special stack. It's going to be actually a double-ended queue. We're also going to define an index equal to 0. We're also going to define the length of our push stack, or pop. It doesn't really matter. So we're going to find all those three. We're going to actually put all this in one line, but it's easier to read. So what we should do is iterate through the push stack. So we're going to iterate through the first stack, and then perform there's two ways of doing it. We can iterate through the pop stack or the push stack. This way is a bit longer, but if we iterate through the push stack, then we want to know a couple of things. So for each position, for P in pushed, what we're going to do is append it to the stack. And each element of push into stack. So while the stack is exists and the stack at the last index, -1, equals pop. So what we want to find is whether the last index is equal to the pop index at I, right? Where I is index 0. So we want to make sure that each element, that's the last element of each stack, is equal to the pop index. That means that we could pop it from the stack because it matches. So stack.pop, and we want to increment our I as well because we have a condition. We need a terminating condition, and then that's pretty much it for our loop here. What we want to do now is return not stack. So if the stack is empty at the end, then therefore we are able to return true. And there you go. Because that means we're able to push and pop everything outside the stack, and therefore the stack remains empty at the end of all this operation. Let's run that. Submit it. So time complexity is big O of n squared for each element inside the push stack, for each index inside the pop stack. That'll be big O of n squared, I believe. Memory complexity is big O of constant space because we return the stack if it's empty. I'm not sure if it's actually constant space. It might be big O of n. Yeah, big O of linear space actually. Alright. Oh, actually no, return true or false. So yeah, no, it's big O of constant space. Alright, there you go. Have a great day, guys.